Today we have David Dunsky from NYU, and he will talk to us about production of ROMP dark matter. Please.
Thank you. Thank you very much for the opportunity to be here. It's good to be back in Texas and good to be back in College Station. I was telling Kevin, this is my second time I've been here. I grew up in Dallas, so in middle school, we actually had a Texas field trip. And so we went to some of the different cities in Texas. And the presidential library here and in Austin were definitely the highlights of that trip. So I wish we could see the Foucault pendulum. That would have been really sweet, but I guess it wasn't around by then. Kevin, you said this building is 10 years old?
You were in middle school about 10 years ago, right?
A little, you're making me feel old. A little more than 10 years ago. So I guess it was close, but anyway, it's cool it's good to be back here. And this time they're talking physics rather than Texas history. So I want to tell you a little bit about some ongoing work with Josh Ruderman at NYU and Sonia Eba at McGill on a new framework for dark matter production, in which we call ROMPs. So you may ask, what in the world is a ROMP? Well, it stands for rapidly oscillating massive particles. Don't worry, not all slides are going to be like this. And it's something you're very familiar with. It's the idea is a way to produce dark matter via oscillating from one interaction state to another. And I say you're familiar with this because oscillations are very familiar within the standard model itself. So you can have, as an example, active neutrinos can oscillate from one flavor to the other, like an electron neutrino produced in the core of the sun can oscillate into a different flavor, like a muon neutrino, by the time it reaches Earth. There are other examples in BSM frameworks. Probably the most prototypical one is active neutrinos oscillating to sterile neutrinos, all of the famous Donaldson-Woodrow mechanism, or the sheaf-Fuller mechanism, which are really two sides of the same coin, and I'll explain those a little bit later. But oscillations don't have to be between fermions. You can have photons can oscillate into dark photons. People have looked into this for resonant conversion from the CMB and so on, and they potentially could be a dark matter candidate. Photons can also oscillate into axions if there's some background magnetic field, or into even gravitons, which is just actually a standard model effect of this Gerstenstein effect, if I'm pronouncing this right. But my point is that these oscillations between different types of particles happen within a standard model and many BSM frameworks. It's a very common scenario, which is why I just highlighted all these different examples. And I want to also emphasize that these oscillations can be a really good way to produce dark matter. If one of these states is very sterile, doesn't talk, say, with the standard model, then that means that that state could be an excellent dark matter candidate. But how it can be produced could be from the state that oscillates into it, right? So one of these states could be very active, could be talking to the standard model. It can have a large thermal abundance in the early universe, and just a small amount of oscillations into the sterile state can be an excellent way of producing that sterile state as dark matter. And so what I want to do is I kind of want to generalize this framework and look at what are the necessary ingredients for this kind of production for these ROMPs, these rapidly oscillating massive particles. So I'm going to talk about again and again two things. First is that if we're going to have an oscillating system, what we need is two states. Okay, so I'm going to talk often about psi, and psi is going to be my interacting state. It's going to be talking, say, with the standard model bath. Eventually, it could talk with its own bath if you like. But my point is, it's going to have some interactions. It's going to have some large thermal abundance. And then I'm going to be talking often about chi, which is going to be the two-state partner to this psi state. And this chi is going to be non-interacting. It's going to be very sterile. So it's going to be an excellent dark matter candidate. And if I were to look at, say, the mass squared matrix of this system, shown here below, if it was just diagonal like so, it wouldn't be a very interesting system. I'd have just two independently evolving states, psi and chi. Right? The kind of magic happens when this mass matrix, or effectively this Hamiltonian, has some off-diagonal elements, right? In this case, now you have some misalignment between your interaction and your mass basis, right? This is not the mass basis anymore. So you can say, David, why don't you just diagonalize this matrix, right? That's what you learn in quantum mechanics, diagonalize it to go into the mass eigenstate basis. And you can diagonalize this with some rotation matrix by some angle, say theta naught. But there's kind of two issues, I'd say, with this, which make it a little bit inconvenient. And the reason is, or the two reasons are the following. One is that often in the early universe, the states that are produced are, say, the flavor states. Like you're producing a psi, it's an interaction state, okay? The second, probably more important thing, which makes this basis a little bit inconvenient, the mass basis that is that the interactions, which are going to keep psi in equilibrium, can often generate a thermal mass for psi itself. And what that does is it generates, as I said, it's some thermal mass, some extra contribution to this mass squared matrix. And this term, this thermal mass, is going to be temperature dependent. And so what that means is that at every point in time, you have a different rotation matrix you need to use to diagonalize this matrix. So that can get a little iffy, or make its evolution a little bit trickier. So this thermal mass is going to be give a huge effect in what makes these ROMP systems very cosmologically interesting. Okay, now what type of interactions can psi have with a thermal bath, which keep it in equilibrium or give it a thermal mass? So kind of the idea of this ROMP framework is that you can choose whatever interactions you'd like. We're going to show you kind of just some general features for whatever favorite model you have of what makes a ROMP very special, but just to maybe give you some tangible operators to think about. What I'll often do in the examples at the end is we're going to consider psi having interactions with the thermal bath, say some fermions F, some exchange of some, say, heavy vector mediator with some mass of order this lambda. And so one of the main interactions from, say, an EFT perspective that we're going to think about, just to, again, give you some tangible operators to think about, but again, will be very general in this framework. This would be some 4 Fermi-like interaction, right? If you integrate out this heavy vector, you get some 4-point interaction like shown. Now, what's very interesting about kind of these ROMP systems, and especially these thermal masses, is that you have to be very careful with considering all the necessary operators. So normally, from an EFT perspective, I'd say this is my dominant operator below the scale lambda. It's this dimension 6 operator. I don't really need to consider, say, dimension 8 or even higher operators. But what I'm going to show you is that's actually not necessarily true. And we're going to see why this is. But what we're going to do as well is going to consider the next higher order correction to these interactions. And these come from, when I look at this heavy gauge boson propagator, remember there's additional pieces that go as some momentum squared over this mass of my heavy vector squared as well. And so if you just Taylor expand this about momentum over mass, you'll get just a normal 4-point interaction piece, which gives you this dimension 6 piece. But then there's also some momentum squared over additional factors of lambda squared that give rise to, say, to some dimension 8 operator. So from an EFT point of view, what we're going to actually have to as well consider is some higher dimension operator, say this dimension 8 operator, shown again from this heavy vector gauge boson. So again, these are just some examples of what we're going to consider for at the end when we're going to look at, say, some example of abundance calculations. As a general framework, you can consider whatever operators you would like that keep psi in equilibrium, and I'll show you how that affects the abundance of chi as dark matter. So as an example, you can consider maybe psi scatters with a heavy scalar. This gives rise to some different physics, but again, within the general framework, it will be there'll be some similarities that I'll share. Okay. So how does this thermal mass, or why does this thermal mass affect this ROMP system very importantly? Well, what it does is it actually sets a new temperature, a new dominant temperature production for this ROMP system, which is kind of one example of why a ROMP is somewhat of a general nice framework for dark matter. In the sense how it frees out, the dominant temperature production is, say, like roughly a mass over 20 or mass over 10. Freeze in may have some dominant temperature production at some UV scale if it's some UV dominated operators, higher dimension operators, or it may have some a dominant temperature production at some kinematic threshold. So for ROMPs, there's a new temperature of production that's very different. And to see where this comes from is let's look at this mass squared matrix as shown here. Right here, I've got this thermal mass piece, as I said, which is very important. And just qualitatively, say we're dealing in the early universe, this thermal mass squared can be huge, right? So it can be way bigger than all these other non-temperature dependent elements here. And in that case, your mass squared matrix is basically one giant element here in this top left compared to everything else. So your matrix, as you can think about, is nearly diagonal. So if it's nearly diagonal, that means the mixing between your two states is negligible, right? Qualitatively, you can think about it like that. More quantitatively, you can see by looking at the mixing angle, tan of 2 theta, which is twice the off diagonal elements minus the difference between the diagonal elements. you can see that when your thermal mass squared is huge, especially compared to your psi and chi mass squareds here, your mixing angle is 1 over a very large number, i.e. it's very, very small. So again, the mixing, which tells you basically how aligned your mass and flavor eigenstates are, how easy it is to oscillate from one state to the other, is totally negligible in the early universe when this m thermal squared is huge, right? But again, this thermal squared piece is going to have some temperature dependence, which will change when this dominant temperature production occurs. So to see this, let's look at, just remember from quantum mechanics, the simple probability of oscillations from one state to the other. And that probability is going to go to something like sine squared of 2 theta, where that's your mixing angle, which again can have some temperature dependence, and 1 minus cosine of your oscillation rate times time. Now, if your scattering rate, which is how you make these quantum mechanical observations, every time this psi state scatters in the early universe, you're making some quantum mechanical measurement, and there'll be some sine squared of 2 theta probability of measuring your psi as a chi if your interactions or if your interactions every time you're making a measurement are much slower than the oscillation rate. So on average, this term averages out, and so your probability, you make a scatter, you make a measurement, is sine squared of 2 theta of measuring your psi as a chi, right? So then that tells us that the number of chi that you get at a given point in time is going to roughly be the probability of measuring your psi as a chi times the rate at which you do your measurements, your scattering rate, times the time you're looking at, which is roughly 1 over Hubble, times your number of psi that you have. Now, typically, if we're dealing with, say, some like normal like freezing, where this guy is not there, this scattering rate over temperature, over Hubble, your scattering rate times time, is going to be, say, very UV dominated. It's going to be very high, some temperatures, some very large power. This is UV freezing, right? But this is not what happens, because here we have some sine squared of 2 theta coefficient up front. And as we've shown here, if this thermal mass squared piece is ginormous, this suppression can be huge compared to your scattering rate. It can be so large that if this is a very large temperature dependence, that your number of chi is very IR dominated, it becomes, right? So if this thermal mass suppression is a larger suppression in temperature compared to your scattering rate times 1 over Hubble, then your production is IR dominated, okay? So you want to you're producing more and more chi at lower and lower temperatures. Something interesting happens though, when sine squared of 2 theta stops getting any temperature dependence, which you can see occurs when your thermal mass squared drops below your m psi squared minus m chi squared. And that time, or that point in time, your mixing angle becomes just your normal vacuum mixing angle. There's no temperature dependence anymore, right? In that case, this term is a constant, and now you're back to UV freezing. So you're UV dominated at production. So there's an interesting point in temperature, which we call TOS, when your thermal mass squared is larger, or I should say is equal to the mass difference between psi squared and chi squared, when the temperature of production is dominated. So at temperatures above this TOS, when m thermal squared is much greater than m psi squared minus m chi squared, you are IR dominated. And when m thermal squared is much less than this, i.e. temperatures below TOS, you're UV dominated, which means that you're dominated at TOS, okay? So that's the new temperature of production, which quantifies kind of the general framework for these mixing ROMP-like systems. Another very nice feature about these ROMPs is that depending on the relative sign of your thermal mass squared and m psi squared minus m chi squared, you can have an actual resonance effect. So you can see that if m thermal squared is exactly equal to m psi squared minus m chi squared, then tan of 2 theta goes to infinity, right? Your mixing angle, sine squared of 2 theta, goes to 1. A very brief moment in time, you can get even a larger production of ROMPs of your chi state as dark matter. So you get these resonances, which are just called Landau-Zenner-like resonances. And I'll show you how you calculate these thermal masses and you do these Landau-Zenner probabilities. Yeah, Kevin?
You may address this later, but how does this story change when the interplay between the interaction rate and the oscillation rate is different?
Yeah. So I'm going to take, like right now.
Oh, beautiful.
Yeah. So there's a caveat to that. And this is another very nice feature about ROMPs. And that's, there's a different regime you can be in, which is called kind of the quantum Zeno regime, right? Kevin, this is what you mean, right? Now let's go back to this probability of conversion, which is going to be roughly sine squared of 2 theta times this again, 1 minus cosine omega os times time. If, however, your scattering rate is so fast compared to your oscillation rate then what happens is you don't average out your cosine omega t, right? Every time you're scattering, you keep seeing your psi state. It doesn't have time to oscillate into a chi. And so your production of chi is suppressed every time you make a measurement. And just to quantitatively actually see the scaling of this suppression, and I'll show you exactly how it comes about more rigorously later, is that if your scattering rate is much larger compared to your oscillation rate, so roughly omega os over t, where t is now 1 over your scattering rate, this thing is a very small number now because my scattering rate is much larger than omega os. So you can Taylor expand this, and you see now that your probability is not just sine squared 2 theta, it's sine squared 2 theta times omega os over your scattering rate L squared. So you're suppressed by this value when your scattering rate is very large compared to your oscillation rate, right? And when this is literally, it's like the quantum Zeno effect. You keep watching your state, you keep scattering, and you're stuck in a psi state. You can't produce this as a chi. And again, this gives rise to a dominant temperature production, not necessarily TOS, but which is when, again, the thermal mass squared is equal to the mass difference squared. But it's when your scattering rate starts becoming slower than your oscillation rate, i.e. you have to be rapidly oscillating for any of this production to occur, hence the name ROMPs. Funny enough, we actually came up with ROMPs before we realized this quantum Zeno effect, so it was like kind of meant to be. So again, there's this new temperature production in some of your models where your scattering rate, your production is dominated when your scattering rate and your oscillation rates are matched. And that's what we call this T Zeno temperature. And again, at high temperatures, you're suppressed by this omega os squared over lambda squared. And at low temperatures, you're again, UV dominated, it's just UV freezing. So you're dominated at this temperature production when your scattering rate and oscillation rates are the same. So those are kind of two different regimes, and it depends on the models you look at, and we'll talk about some examples with like this heavy vector exchange. Okay, so what I want to do kind of now is go over this framework of how you actually can capture all these different effects, these oscillations, these scatterings, i.e. these measurements, these resonant lambda center-like resonances, and these in medium, i.e. thermal mass-like corrections, which are very important, as we just shown for setting what the mixing angle is, the temperature-dependent mixing angle. We want to figure out how you can kind of combine all these effects to determine the relic abundance of your chi dark matter and the associated constraints. And so what you need to do is you can't just evolve the normal Boltzmann equation. It's just as evolving these like semi-classical probabilities. You have to actually evolve these the full density matrix, von Neumann equation, which accounts for as well these quantum mechanical like resonances and coherent like effects. And what you can do is again is this density matrix evolution equation, which you're familiar with from quantum mechanics. But there's a really nice way to visualize this due to Dunsky, which is to go kind of to decompose this density matrix into kind of a more block sphere-like approach. And I think this geometric visual is really helpful to understand how all these effects of like resonances, oscillations, and scatterings all affect this ROMP two-state system. And so the idea is with this density matrix, which includes your ROMP state and all of the background medium, you can trace out the background medium until you just get a 2x2 effective density matrix. And so any 2x2 matrix, I can always expand as a sum of the identity matrix plus a poly matrices, right? This is just a fact that the poly matrices and identity are complete. So you can just write it as so, okay, as some P naught plus a P dot sigma. And we can determine what these coefficients are. Because the poly matrices are traceless, you can take the trace of this guy to get what the coefficient of P naught is. It's just a trace of your density matrix. But the more important point for our polarization vector will be this PZ direction. And to find what PZ is, you just multiply by sigma Z and take the trace. And you can see when you do that, we'll get the trace of rho sigma Z is the rho psi element minus the rho chi element. If you remember from quantum mechanics, your density matrices, the diagonal elements, are basically related to the classical number of particles you have in that system, right? So this is effectively the density, the distribution function of psi minus the distribution of chi. Okay, so that's what this polarization, this PZ direction tells you. So as an example, say your ROMP system is entirely, starts off entirely as psi's. So you have no chi's to begin with. What that tells you is your polarization vector PZ points entirely in the Z direction. Alternatively, if your ROMP system is all chi's, your polarization points in the negative Z direction. okay? So the geometric picture is that you have this polarization vector on this block sphere, on this abstract sphere. When it points in the north pole direction, you're entirely polarized as a psi state. When it's in the south pole, you're entirely polarized as a chi. When it's some off axis, you have some linear combination of psis and chis, okay, some superposition. And when your psis and chis are exactly equal, your PZ is 0. And you're entirely, when you have no polarization vector left, you're entirely in a mixed quantum state, okay? So this kind of nice geometric picture just tells you a nice visual way of saying how your ROMP system is behaving. So what we'll do is we'll actually look at this evolution equation in terms of this polarization picture, which is again due to Dunsky and this Occhiezer in 81. And what you get is some evolution equation, entirely equivalent to the von Neumann equation, for your polarization vector evolution, which has some gyration-like piece, some damping piece, and some production piece. And so let's look at each one by one and see how that affects your ROMP system and how you get all these oscillations and dampings, scatterings, and resonances from this geometric picture. Okay, so first, let's look at this first term, omega cross p. So this is basically just a gyration evolution equation, okay? The important thing is for this omega, what you can show, it's called this ROMP mixing vector. It acts like a magnetic field, like a spin in a magnetic field. And the point is that this omega has a magnitude equal to your oscillation rate. The oscillation rate is just a difference in your energy eigenstates. The more important thing is that it's some vector shown here in red that's off my axis at an angle 2 theta, where this theta is exactly that mixing angle I was telling you about previously. Okay, so it tells you how aligned your mass your mass or your flavor eigenstates are. How close to being diagonal are they? Okay, so let's look at this first term, this dp dt cross equal to omega cross p. That's just this gyration equation. And what it tells you is that if your polarization vector starts entirely polarized as Z, i.e. you're entirely polarized as a psi state to begin with, it's going to gyrate about this magnetic field-like vector. And its PZ will slightly decrease as it gyrates, i.e. you're oscillating briefly into into chis, and then back to psis again. And this is just the evolution of this projection of P along the Z direction. And from this PZ, you can figure out what the distributions of f psi and f chi are. And you can show analytically as well, or numerically as shown here, is that f chi over f psi, your initial f psi, which you can interpret as a probability of psi converting into chi, is exactly equal to the standard quantum mechanical probability of conversion. So this term right here basically tells you just the standard quantum mechanical oscillation effects, right? Now, I've been saying that this mixing angle is temperature dependent. So what that means is that this magnetic field changes with time, right? It's going to move on this block sphere with time. And we've just shown that this polarization vector of my ROMP system gyrates about my effective magnetic field, right? This magnetic field with an angle 2 theta. So here's a question is like, what happens to this ROMP polarization vector as my magnetic field changes along the block sphere? Does it keep gyrating about it? Does it follow it? Yes or no? And let me show you what kind of an example of what happens is that if your magnetic field, or if your mixing angle, I should say, changes relatively slowly with time, say it goes from the North Pole to the South Pole, which happens when you cross a resonance, sine 2 theta becomes small, goes to 0, and then back to, pi over 2 goes to 1, and then back to 0, i.e. it flips from North to South Pole. If this process is slow enough, then your ROMP polarization vector can actually gyrate and follow it, and it gets entirely flipped into the South Pole, i.e. it becomes polarized now as a chi state dominantly. Okay, so this is what's called adiabatic resonant conversion. It's basically level crossing. It's what's happening. And if this process is slow enough, the efficiency at which you're polarized from the north to the south pole, i.e. you're flipping from a psi to a chi state, can be extremely efficient. And what you can show is that with this f chi over f psi to begin, the initial f psi, which again you can interpret as a probability of conversion of psi to chi, follows what is called this Landau-Zenner probability of conversion, where this gamma factor is called this adiabatic parameter, and it tells you effectively how fast this resonance occurs, how quickly your angle changes with time. And what it is the time at which you're on resonance which is a time when your mixing angle is at pi over 2, i.e. in this equator shown here, relative to the oscillation timescale, which is kind of the internal clock of your ROMP system. So if your ROMPs can oscillate many times within this resonant, when the period at which this angle changes with time, then the ROMP system sees adiabatically this change of conversion, and this gamma factor can be huge, which means that your probability of conversion can be extremely efficient. So you get 100% conversion of your psi to your chi states. Okay, so this is a very efficient way of producing chi as dark matter. However, what often happens is that your resonant width, how quickly your mixing angle changes with time, is typically much faster than your oscillation rate, and so your ROMP system can't fully see that resonance, and so it's a non-adiabatic conversion. And this gamma is less than 1, at which case you have some exponential suppression. Roughly speaking, your probability is this pi gamma over 2 when you do this Taylor expansion of your exponential. So again, this goes by this Landau center probability, and it's this quantum mechanical, again, effect of converting psi to chi, which can happen when your mixing angle goes to 1 very briefly. All right, now let's look at this other term here. This is a damping term, which you can show is equal to basically your 1/2 times your scattering rate of psi in the early universe. So this is kind of what we were looking at previously, where every time psi scatters, you're making some quantum mechanical measurement, and you have roughly the sine squared of 2 theta probability measuring your psi state as your dark matter chi. Okay. Now this damping term again goes as your scattering rate, but it goes as this perpendicular component of your polarization vector, meaning your polarization vector in the xy plane. So if your polarization vector is entirely pointed in the z direction, or the negative z direction, i.e. it's entirely polarized as your psi or your chi, every time you scatter, you're always going to see that as a psi or a chi. It's because it's not a linear superposition of states, it's just a psi. So every time you measure it, you're still going to find psi. What happens is that you need to go off axis, you need to have some linear combination, a linear superposition of your states, such that when you make a measurement, you're now getting that sine squared 2 theta probability of being in your psi state, or excuse me, being in your chi state. So what this term does is that it reduces your polarization vector and makes your system more and more of a mixed state whenever you have some oscillations, and every time you oscillate, you're making some, again, quantum mechanical probability, quantum mechanical measurement of seeing your psi as a chi state. Okay, so what you can show is that this term gives rise to a Boltzmann-like equation where the rate of change of your chi dark matter is equal to your probability of conversion times the rate at which you're making your quantum mechanical measurements, right? And so you become, if you have infinite amount of time, you become more and more of a mixed system, and you can keep building up your chi as dark matter. All right. So kind of just to summarize, from this von Neumann equation, we have actually some effective like Boltzmann equation that captures all these different limits, which is much more numerically easy to solve. And you have some kind of scary looking equation shown here. But what it does is it actually captures all the different effects I talked about. So this first term here gives rise to these transitory oscillations of your ROMP system. Whenever your scattering rate is negligible, what this gives rise to is just your normal vacuum oscillations or normal oscillations. This term here is this quantum Zeno effect I was telling you about. If your scattering rate is much larger than your oscillation rate, this omega, then you're suppressed in your probability of conversion by a scattering rate over oscillation rate squared, which is just what we expected from this Taylor expansion. Yeah.
So, if I have a little bit larger m psi,
If you have a little larger m
psi.
psi. Yeah, yeah.
So is that scenario also covered in?
Yeah. So so you can, right. So you can have m chi psi as a variable, or you can have sine of 2 theta as a variable, right? Sine of 2 theta tells you how big your m psi chi is, right? In fact, m psi chi will generally be a constant. It's not temperature dependent. So that's related to the vacuum mixing angle. So that's captured in here, your sine squared of 2 theta. So you can either have sine squared of 2 theta as a variable or m psi chi as a variable in some sense. So what I'm doing is whenever you see m psi chi, that's built into the sine squared of 2 theta. So it's related in particular to the vacuum sine squared of 2 theta, right? So I'll show you at the end of the day, the results for dark matter as a function of sine squared of 2 theta naught, the vacuum mixing angle, right? Because that's an input to your theory, right? I.e., what is your m psi chi? Yeah. All right. Okay, good. So this captures this quantum Zeno effect. And then this piece is kind of the standard way we think about kind of production of chi dark matter, which is every time psi scatters with the background particles, there's some sine squared 2 theta probability of measuring that state as a chi. And so you keep scattering, you keep building up your chi. Again, if up to these quantum Zeno suppressions and Landau center-like resonances. Okay, and for these resonances, as I was saying, this sine squared of 2 theta, right? This is the temperature dependent. It's a in medium mixing angle. You can write this in terms of your vacuum mixing angle, or m psi pi, right? Which is a fundamental input of your theory. It's just a constant. So you can write this in terms of your vacuum mixing angle over this thermal mass squared suppression. Thermal mass squared over your delta m squared. So as an example, when m thermal squared over delta m squared is exactly equal to cos 2 theta naught, then this piece becomes sine squared 2 theta naught over sine squared 2 theta naught, i.e. becomes 1. That's the resonance, as I was saying. So it depends on the relative sign of this guy to this guy, right? If still, which again occurs at this temperature T-os, if the relative sign is not exactly cancels, the temperature is still dominantly produced at T, the chi is still dominantly produced at T-os, except your sine squared 2 theta doesn't briefly go to 1. It just goes to your vacuum mixing angle very quickly. So again, this relative sign determines whether you have these resonances or not at T-os. And you can actually integrate this equation across the resonance, and you get exactly the Landau-Zenner probability of conversion to leading order. So this kind of Boltzmann-like equation actually captures this full quantum kinetic equation shown above very, very well, but it's just a little bit more numerically easy to solve. So this is a nice feature that we have for our models.
DP?
Yeah. So, right. So you see, it doesn't look like there's any Hubble in here, right? But what you can do is this d dt, right? You can write in terms of partial HP, right? And so what you do is to numerically solve. So that goes on the left side, right? And what you do numerically to make this mostly convenient, to make it very convenient, is whenever you see momentum, just go to co-moving momentum. And you go to co-moving momentum, right? The Hubble HP term cancels, which just makes this like a normal flat space evolution equation. But yeah, Hubble is in here, right? If Hubble was not in here, then you would always be able to scatter indefinitely long, and you keep building up your chi, and you would always reach equilibrium. But Hubble prevents that from happening. Okay, and we'll talk about that. All right. So before actually going into this example calculation with, say, this heavy vector, I want to go over very quickly, or I want to go over first this thermal mass, which is, as I was saying, extremely important for setting your temperature-dependent mixing angle. And for a general framework, we wanted to show people how you can very simply calculate this thermal mass for whatever favorite model you have. To do this, I'll show you an example with, say, just photons forward scattering. But one way you can calculate these thermal mass effects is you can do these scary looking loops and so on in thermal field theory. There's a really nice equivalent way of doing these thermal masses, which is actually just calculating standard tree level matrix elements. You can like chapter 5 Peskin Schroeder, you can look that up and you can calculate these thermal masses very simply. And what you can show is that your thermal mass squared is equal to just a forward scattering matrix element. By forward scattering, I mean that psi, the initial state of psi and the final state of psi are exactly the same. The background particles that psi scatter with and the background particles that psi scatter with are the same before and after. That's what I just mean by a forward scattering matrix element. So the thermal mass squared of psi, which comes again from thermal scattering, from forward scattering with the background medium, is just equal to this matrix element times your number density of background particles over roughly your energy of your background particles. And when I put these parits, I just mean average over the distribution of background particles, which may have a thermal distribution or not. So just to emphasize, thermal masses, you can think about, they're really in medium masses. It just happens that the medium has temperature. So that's why we can call them thermal masses, but it's just coming from forward scattering with any background particles. So photons background scattering with like glass or atoms gives rise to index of refraction, which you can think about, those are effective masses, or these thermal like masses, equivalent picture. Okay, so let me show you an example of how simple this is to use this formalism to calculate these thermal masses for, say, whatever favorite model you have. let's just look at photons, right? What is the immediate mass of photons coming from in a background plasma of, say, electrons? Well, the photons' thermal mass comes from forward scattering with background electrons. So all you have to do is calculate these forward scattering, these matrix elements, which give rise to forward scattering. Again, literally, you can just look up at this in chapter 5 of Peskin and Schroeder. Just parametrically, we can just estimate this, say, in the non-relativistic limit. These matrix elements are going to go of order E squared, i.e. alpha. So this M naught is basically alpha, E and M, i.e. 1 over 137. And background is going to be the number density of electrons. And in the non-relativistic limit, your energy of your backgrounds is just ME. So this is exactly your photon plasma mass squared, right? And you can do this in the relativistic limit if you like, and you can get all the exact, relativistic corrections to the photon plasma mass. So it's extremely simple way to calculating these thermal masses and whatever favorite model you have. And what we're going to do now is actually show how to do this in this first example of a ROMP forward scattering with background fermions from this dimension 6 and dimension 8 operators, right, from this heavy vector. Okay, so now here we're going to go over again this example model of I have a psi chi system. My psi is interacting with the background medium from these heavy vector exchange with fermions as shown here. And what we want to do is we're going to want to first calculate the thermal mass so that we can calculate TOS, right, or T0 if we like. Right, TOS is again set by the thermal mass squared is equal to the mass difference of psi and chi. So we need to know what this thermal mass is. All right, so let's just say we have this dimension 6 operator, which is giving rise to psi forward scattering with the background fermions. And let's calculate the thermal mass of psi from this interaction. Okay, so we can parametrically estimate what this forward scattering matrix element is. It's going to be 1 over lambda squared, and then to get the right units, you need to be t squared up top just for energy. So m naught is something like t squared over lambda squared. My number density of background particles, I'll just write as number density of fermions. And my energy of my background particles, I'm assuming this is all relativistic, is going to be something of order t. Okay. Now, if that was it, then that would be my thermal mass for psi in the early universe, but that's not it. And the reason is psi can also scatter with antifermions in the background plasma as well. And here's just kind of a beautiful thing, is that from this matrix element, it actually flips sign when you scatter between fermions and antifermions. Okay, and what that means is that the total thermal mass is equal to something that goes as NF minus NF bar. And this can actually be very small in the early universe. In fact, this is very analogous to if you take lambda to be at the weak scale, this is how neutrinos get a thermal mass in the early universe. And this is the dominant piece you expect, is the dimension 6 piece, but it's actually can be very small because the lepton asymmetry may be very small. And in fact, Donaldson and Woodrow in their original work neglected this piece because they assumed that NF minus NF bar was small. Okay, so all this comes about is very simple to see, is because your matrix element, forward scattering matrix element, flips sign when you scatter between fermions and antifermions. And so that's why we're going to need to go to the next order piece, this dimension 8 operator, which may not necessarily be small, even though you think it would be because it's suppressed by lambda squared. And when you calculate this, let's look at this dimension 8 piece, the forward scattering contribution to psi from this dimension 8 operator. Well, again, it goes as something 1 over lambda to the 4th. To get the right units, I need t to the 4th. My energy in my background is still t, and my number density of background particles is going to go as NF. But when you forward scatter with antifermions now, because there's additional momentum pieces, if you remember, when you forward scatter between fermions and antifermions, the 4 vector goes like k goes to minus k, right? And that sign flip changes the sign flip from when you do the fermion commutation. And it makes the matrix element be the same sign when scattering between fermions and antifermions. And so the dimension 8 contribution of this thermal mass for psi goes as NF plus NF bar, and that may not necessarily be small. And this is the actual contribution that Donaldson and Woodrow looked at for their thermal mass effect. Okay. On top of that, you can see from this whether or not you get a resonance depends on the relative hierarchy, mass hierarchy between psi and chi. So really, a cute feature of ROMPs is that by just changing very simple things, like the mass hierarchy of whether psi or chi is heavier, tells you whether or not you can get resonances. So like in the standard neutrino picture, where I have an active neutrino, it's very light compared to a sterile neutrino, right? Like Donaldson and Woodrow. If you look at this, your psi, which is like your active state, your neutrino is very light compared to your sterile state, your chi. And so your denominator of tan 2 theta goes as m thermal squared minus m chi squared, roughly speaking. But for neutrinos, right, the dimension 8 piece is also negative. And so this denominator will never cross 0, right? It's always negative for that mass hierarchy. For if you assume there's a large lepton asymmetry, which has the opposite sign, you can get a resonance, right? M thermal squared and m chi squared have opposite signs. You can get a resonance. That's the Sheaf-Fuller mechanism. So Sheaf-Fuller and Donaldson-Woodrow are literally the same thing, except Sheaf-Fuller assumed this dimension 6 piece is large, right? They have this large lepton asymmetry, and coincidentally, the sign of that matrix element relative to the mass hierarchy for neutrinos and sterile neutrinos is such that this denominator can blow up, i.e. you can get a resonance. It doesn't work for Donaldson-Woodrow. Question?
Maybe extending the analogy to neutrinos, is this in essence just equivalent to making a temperature-dependent MSW effect?
Oh, yeah, the MSW. Yeah, so the MSW effect is, they're looking, if this contribution is the MSW effect, but the MSW effect occurs in the late universe, right? Like say in stars, there's no anti-fermions around. So this thing, you have a large lepton asymmetry, right? So exactly, the MSW effect is this is the dominant piece. But in the early universe, this is not negligible, and that's why it's small. Unless you assume there's a large lepton asymmetry, which is what Sheaf-Fuller do, right? But there's bounds on that, so it doesn't work too well. But Donaldson and Woodrow say, let's just take the lepton asymmetry to be very small. And so they look at this as the dominant piece. But exactly right, MSW is this piece, but because there's just no positrons around, it's just always the biggest contribution. Yeah.
Can I add just that, that's the reason why we see a resonance with neutrinos only when delta m squared 2-1 in the sun is positive, right? Like that's why you can unlock the ordering of the neutrinos, the same exact reason of chi squared, or sorry, psi squared minus chi squared.
Right. Yeah.
So just for the consistency, I could have done the same calculation going to the psi 1, psi 2 basis. So I can like first go to the mass basis.
The mass basis, yeah.
And I calculate like because now I will have 2 mt1 square, mt2 square. And in that also, when I take the expectation value, calculate the new m0, the results will be same irrespective of what the value of m psi square minus m chi square versus m psi chi square is.
Yeah, so these are right. These are I wrote purposely in the flavor basis, but you could redo this in the mass basis, right?
So now I will have like two thermal corrections, right?
Well, it's I mean, it's tricky. Yes, it's trickier because you're doing mass basis and you have contributions to both. That's why doing this in the flavor basis is easier. Just pick both sides. I mean, to pick which pieces get thermal corrections and which don't, right? But the physics has to be the same. You can do this in the mass basis if you like, right? Yeah. So you still get a resonance in that case.
Okay.
Right. You get what's called avoided level crossing, right? And you can do standard like Landau center like formalism and calculate that in the mass basis if you like. The physics has to be the same, right? It's just easier. I think it's easier to see whether you get a resonance or not in this basis.
But basically, you are saying like it doesn't really matter even if like my m chi is like the difference, and then the basically this ratio becomes 1, and even at 0 temperature it doesn't matter. Like this is consistent throughout all the possible angles.
Oh, well at zero temperature, right? Well, this piece is always. I mean, this piece is negligible.
Yeah, so I'm thinking
right?
like in that sense, like my basically like the offset, like the octagonal entries, and like basically what Bhaskara asked.
Yeah.
So I was wondering like if I go to the mass basis, because there I'm like definitely sure that throughout the hierarchy, like no matter what the hierarchy is, like my value will work. What you are saying, this will also work.
Yeah, I think maybe we can talk offline, but the physics should be the same, but yeah. But I want to emphasize, as Kevin was saying, if M21 was different, right, then you could get a resonance or not, right? The same thing here is true for us. For a ROMP system, you can choose whether your mass hierarchy, whatever you like. So you could choose your chi state to be lighter than your psi state. In that case, you can get a resonance on this dimension 8 piece that you would not have normally gotten for the standard Donaldson-Woodrow. And on top of that, it actually helps you with constraints, because one of the big issues with Donaldson-Woodrow is that your sterile neutrinos can decay to active neutrinos because they're heavier than your active neutrinos, right? The same mixing angle, which gives rise to their production, also gives rise to their downfall. But for this opposite hierarchy, you couldn't have that decay channel. It's not kinematically allowed. So there are very simple things you can change, which gives rise to very different phenomenology, which is very nice. Okay. Let me now, okay, so we've just calculated this thermal mass. Let's focus on, let's assume there's no lepton asymmetry. It's very small. So let's look at, let's just take the dimension 8 mass, or dimension 8 thermal mass to be the dominant thermal mass, i.e. this guy right here. And now let's just show explicitly that the dominant temperature of production is at this TOSC when your thermal mass squared is equal to the mass difference of psi squared and chi squared. Okay, so let's calculate the first is gamma over h, which is basically how much your scattering rate times your time at which you're scattering. So your scattering rate, since this dimension is this heavy vector exchange, will go something as c to the fifth over lambda to the fourth. Hubble goes as t squared over m plane. So gamma over h goes as t cubed. And if that was the only effect, that would tell you have UV freezing, right? Your temperature, your dominant temperature of production is as high temperature as you can get, right? But again, we're suppressed by the sine squared of 2 theta. And when temperature is much greater than TOSC, your m thermal squared is much greater than delta m squared. And so this thing at T much greater than TOSC, you can see goes as 1 over m thermal to the fourth. And m thermal squared goes as T to the sixth, right? It's T cubed, and then NF also goes as T cubed. So this goes as T to the sixth. And so what this tells you is sine squared of 2 theta above temperatures greater than TOSC goes as 1 over T to the 12th, right? Very, very suppressed. And so T cubed over T to the 12th is extremely IR dominated, right? You see? Let's look at now when temperatures are much less than TOSC, i.e. this term is small relative to this. And then we're left now just then with the in-medium mixing angle is exactly equal to the vacuum mixing angle, sine squared of 2 theta naught, it's a constant. And so therefore, gamma over h times sine squared of 2 theta just goes as t cubed. So it's UV dominated, right? So if it's IR dominated above TOSC and UV dominated below TOSC, it's dominated at TOSC, right? So that just shows explicitly that the temperature dominantly is produced at TOSC. What actually is TOSC? It's very simple to calculate from this. Right, it's just when m thermal squared is equal to m psi squared minus m chi squared, which I'm just going to take just right for simplicity as the max of m psi squared or m chi squared. So all you do is literally set this guy equal to that, and you can find the temperature at which this occurs. And it's some very weird looking temperature. It depends again on what this lambda is, or the mass of m psi squared and m chi squared. But it's shown something like here. So this is kind of in the Donaldson-Woodrow, if you ever see what temperature the sterile neutrinos are dominantly produced. Lambda is the order of the weight scale, so about this guy right here. And chi is your sterile, is heavier than your psi, your active. So this thing is like, say, KeV. If you plug this in, you'll get something like 100-ish MeV or so. And this is what it's in Donaldson-Woodrow. So it's this very random looking temperature, but here you can see exactly how it scales with your parameters, okay? And now what we want to do is now we know what TOSC is. Let's go ahead and calculate this abundance of chi dark matter. And we have these, again, these two effects, these very simple scenarios when chi squared is heavier than m psi squared and when it's opposite, okay? So the first case is kind of like your Donaldson-Woodrow-like case, where your sterile state is heavier than your active state. And then this opposite case is not Donaldson-Woodrow-like, okay? Again, this goes back to whether we have a resonance or not. For here in this case, right, psi squared is always lighter than chi squared. So your tan of 2 theta is basically this, it's always negative. And so if you were to plot sine squared of 2 theta, it looks something like this as a function of temperature. At TOSC is when it starts reaching its vacuum mixing angle, something like this. Now, in the opposite case, the opposite hierarchy, you have a sign flip. So psi squared is greater than chi squared. And so therefore, just write it like this, you can have a brief moment in time where your temperature, when your m psi squared is equal to this t cubed over lambda the fourth term, and your resonance blows, and you have a resonance, and your mixing angle blows up. So you have a brief moment when your mixing angle goes to 1. And so you have a resonant effect there, which you have to check. This Landau-Zenner contribution. Question.
Interesting, where like m psi and m are very close to each other, much greater than m.
Yeah, so this is a very interesting case where you have some near degeneracy, right? So you can have different interesting physics there. So the kind of the models I'm considering, I'm just assuming one is bigger than the other parametrically, but you can have different physics. You have to be a little bit careful with when there's a very small degeneracy. Yeah. Okay. So what that means is that in this first case, we just have to calculate these incoherent scatterings of production at TOSC. Whereas in this scenario, we have to also calculate this Landau-Zenner resonant-like production at TOSC. Likewise, we have different phenomenology, and in this hierarchy, you have to worry about the lifetime of your chi dark matter because it's heavier than your active state. Whereas in the opposite case, you don't have to worry about the lifetime, which is nice, but you actually still have to worry about a different process, which can give the more dominant production of dark matter, and that your psi can freeze out and then decay to chi. Okay, and that can actually give you more dark matter of chi than this oscillation production. So you have slightly different phenomenology, but both are doable to solve for. Now, what I'll show you is the actual numerics and the results. But just in your models, you can very simply parametrically estimate these yields, right? And that's very simple to estimate. The yield of chi is going to be the yield of psi times your scattering rate times sine squared of 2 theta over Hubble at TOSC. At TOSC, sine squared of 2 theta is basically sine squared of 2 theta naught. And this formula gives you parametrically a very simple way to estimate your yield of chi, which you can use to find dark matter. Now, what I'll show is, and this plot here shows the actual numeric solution for the full quantum kinetic equations, but it agrees very well with these simple analytic results. So this x-axis shows your chi is dark matter. Again, this is a case where your chi is much heavier than psi, the non-resonant case. My y-axis shows lambda, my cutoff scale of my theory, or if you want to think about it, typically the mass of your heavy vector that's doing this mediation of psi. And these different contours show the vacuum mixing angle, the input of your theory, i.e. you can write this in terms of m psi chi, that give you the right dark matter abundance, okay? And so the kind of the point is that even for very small mixing angles, you can get the right dark matter, which is kind of what I meant by this ROMPs being a very efficient way of producing dark matter. Now let's start populating this plot with some various constraints. So first, if your vacuum mixing angle is greater than 1, which is not possible, right? Or what happens in this region above here is that you need a vacuum mixing angle greater than 1 to get the right dark matter abundance. So that's not possible. So you just can't produce dark matter in this region shown here. Dark matter is just underproduced. Okay. Now, what about this region here? So since chi is greater than psi, as I said, the mixing angle, which gives rise to its production, can also give rise to its decay. So chi can mix with psi, and then say if psi interacts with fermions that are charged, you can brem off a photon. This is kind of the standard sterile neutrino decay channel, right, where these would be like active neutrinos. And roughly speaking, the bounds are roughly the lifetime has to be less than 10 to 28 seconds. And what you can show here is that chi is too heavy, that the lifetime is shorter enough than 10 to 28 seconds. And for normal sterile neutrinos, which is lambda is about the weak scale, and m chi is, I guess whatever you like, and principal it's got to be above a keV, there is no room for dark matter. So the normal sterile neutrinos cannot be produced via the Donaldson-Woodrow mechanism, okay, because you have lifetime bounds from this X-ray, which are too strong. There is also bounds from producing your active state in supernovas if psi is sufficiently light. So again, psi interacts with these, say, charged fermions in these center model in the center model back in the early universe, as well as, say, the cores of supernova. And these temperatures can reach of order 100 MeV. And for lambda, for cutoff scales less than about a few TeV, you can produce so much psi escaping that the supernova cool quicker than expected, and that is ruled out. Okay, but this is a model dependence. I'm assuming here that F is the fermions that psi scatter with are charged, say, under electromagnetism. Okay, then there's as well warmness bounds. So high dark matter, if it's too light, then you can get distort substructure on sufficiently small scales. And so in this red region, chi is so light that you mess up a small scale structure or large scale structure. Okay. Now let's talk about this resonant case, and then I'll wrap up. In the opposite regime, when your psi is much lighter than chi, then you can have this resonance effect. So you can calculate these Landau-Zenner conversion. And again, in our work, we have very simple ways to estimate what this exact adiabatic factor is, depending on your model. I won't go over into the details, but I'll just show you kind of a plot showing the now Landau center-like probability of conversion. And again, I have the m pi dark matter mass on the x-axis. I found it a little bit more easier to visualize, plotting not lambda, but sine of 2 theta naught, your vacuum mixing angle, your input of your theory. And these different contours show the right dark matter abundance for different values of lambda. And what I want to emphasize, first off, is that your mixing angle in the resonant case can be much smaller than the non-resonant case, i.e. the resonance is just more efficient. So for a given vacuum mixing angle, you can take it to be less than you normally would. So it's even a very small vacuum mixing angle can give rise to a sufficient production of chi dark matter. Now, here's something interesting what happens. If you take your vacuum mixing angle to be too small, then you see what happens is that it doesn't depend on the mass of chi anymore, right? It just is this vertical line. And what's happening there is that when your vacuum mixing angle is so small, you're not able to produce enough dark matter, and the freeze out and decay of your psi to chi is actually giving you rise to more dark matter production. And so in this regime here, in these vertical lines, your vacuum mixing angle is so small that your freeze out and decay is what's doing the dominant production of chi dark matter. Now, in this regime, you also have collider bounds, roughly for lambda less than about a TeV, which is roughly shown kind of, I don't know if it's a little hard to see, but this kind of shaded region over here is roughly ruled out for colliders, but you have quite a bit of parameter space in both cases, a little bit less for the non-resonant case, where you're able to produce dark matter as chi via these oscillations, but still survive from these phenomenological constraints. And what I'll do is I'll just wrap up and say in different models, like if you consider different interactions, you can give rise to different thermal masses and then hence different TOSCs and different effects like quantum Zeno effects, which I talked about briefly. So again, it really depends on whatever model or framework you're interested in. But from this framework, you can easily calculate your dominant temperatures of production, TOSC, T-Zeno, and the yields of your dark matter for whatever model you're most interested in. And you can get rise to different physics in those, depending on the different interactions you consider, i.e. different TOSCs and so on. So just to summarize, what I've shown you is that ROMPs are a simple framework for calculating, I've shown you a simple framework for calculating the production of ROMPs in the early universe. That you have this new temperature of production, this TOSC, where your thermal mass squared is equal to the mass difference of psi squared and pi squared. You can also have these quantum mechanical Landau-like effects, or these quantum Zeno effects if your scattering rate is very fast compared to your oscillation rate. And there's tons of different operators you can consider. I just showed you one simple one with heavy vector exchange, but you can consider whatever operators you like, and you can get slightly different physics, i.e. where Landau center is important in some regimes and it's not in others, or Zeno is important. But again, this whole framework is still mutual to all these different models. And then there's all these very nice signals you can get, such as photons from ROMPs decaying. You get these warmness bounds and collider bounds if this cutoff scale of your theory is too small. So thank you.
So like,
David,
I think when you showed that region for at least for the m chi greater than psi region, like the region which is like left open.
Yeah, the white one here.
Yeah,
Yeah.
this is like the sine theta is not too small,
Yes.
right? But then I should be worried about how I define the rho chi,
How you define what?
the rho of chi, like the diameter density, because like physically the state should not be chi anymore because
Right.
everything is.
Yeah. When you get very close to one, you have to be a little careful, right? I mean, this is still like 10 to the -2 or so, all right? I mean, it's still, the one state is very dominant, but mass eigenstate is clearly one flavor state, roughly
So
speaking.
basically you're saying like maybe near the one I should.
Yeah, the other one you have to be a little careful with definitions. Yeah, right. Yeah, good question.
Why you can check the scalar mediator?
Yeah, so we did that, and what we found initially was that you could get at dimension 6, you can get a thermal mass that goes as NF plus NF bar, which was very interesting. Also we found that you could get Zeno is actually T-Zeno is the dominant temperature production. So rather than TOSC, remember I was showing you at the beginning if the oscillation rate is
How does it?
So it was parametric, just because the thermal mass, the scattering rate in the thermal masses were different. Compared to the fermion, from the heavy vector case, right? But we found some subtleties with this, so we're double checking this. So I don't have a for sure answer with this, because we thought we knew what we were doing with the scalar case, but there's some thermal field theory subtleties that we may have done incorrectly for that. So I have to get back to you on that, but we're working on that. But like very small differences can give rise to like, dimension 6 operator is bigger than dimension 8, and just because of the sign flip, it's very nice. Yeah.
Yeah, intuitively dimension 6 would be good. That's why I asked you.
Yeah, exactly. Yeah.
Also, maybe the light mediators also.
Right. Well, the light mediators, like if you would get more into like you can merge this, or this becomes like normal photon dark photon production, like our oscillations, right? But those are actually dominated at it turns out that since those are dimension 4 operators, which give rise to like the dominant production temperature, because it's very light mediator, are dominated at like the kinematic thresholds, like the electron mass.
But those also would have some temperature correction.
Those do have temperature corrections. Yeah. But yeah, you can play around with the operators, you get very different physics, but all within this general framework. So
This is very nice.
thank you.